Okay, so we have 2 kilograms of saturated liquid R134A in a well-insulated, weighted piston cylinder device. Weighted piston cylinder device. What does it mean? We have R134A. It is weighted piston cylinder device. Then we can do a force analysis on this piston. So what kind of forces are acting on this piston? First, we can think about atmospheric pressure. PATM. And we can think about the weight of the piston. And we can think about the pressure by our system. So if you do a force analysis, so pressure P times area minus PATM times area minus weight should be 0. If we rewrite this in terms of this P, the pressure of our system, it's going to be PATM plus W, weight over area. Then, is this ATM, PATM, a variable or constant? Constant. Weight, variable, constant. Constant. Area, variable, constant. Constant. So whenever you have a weighted piston cylinder device, pressure is constant. So that is a constant pressure process. So whenever you see weighted piston cylinder device, it is possible you can assume it's a constant pressure process. I wish that that this screen is larger than this one. My dream classroom is going to be the entire wall is covered by screen, silly, right everywhere. Or if you install screens everywhere, I appreciate that. How generous you are. Okay, now we know it's a constant pressure process. And there is another word. Well insulated. What does it mean? Adiabatic system. What is adiabatic system? There's no heat transfer. So if that's the case, what is the energy balance equation? Q in plus W in minus Q out minus W out. The right-hand side is mass times U2 minus U1 plus moving boundary work. That is the general form. But if you have a constant pressure process, what is the right-hand side? Mass times H2 minus H1. We assume that there is no heat transfer, well insulated, Q in, Q out, and there is an electrical resistor inside. It's going to provide energy transfer by work, W in. And how can we determine this electrical work? Voltage times current times time. Voltage times current times time, delta T. What about energy transfer by work system? None. So this is going to be mass times H2 minus H1. So let's see, what do we have? Do we know the voltage? Yes, 10 volts, 2 amperes, time t is the unknown, the mass is 2 kilograms, then we just need to determine H1 and H2. That's all. What is H1? The initial temperature is -4, and it is saturated liquid. So initially, T1 is -4, and we don't have to determine the phase change process. It is given saturated liquid. Phase change process number 2. And what happens? Because of this energy transfer by work, this becomes saturated vapor. this becomes saturated vapor. Then what is the temperature? It is constant pressure process. At this constant pressure, I don't know what is the pressure. Let's talk about TH diagram. It looks like this. Initially, phase change process number 2, saturated liquid. So this is the initial state. And because of this heat transfer, at this constant pressure, it becomes saturated vapor. Where is it? Right here. Number 4. What is the temperature of this saturated vapor? T sat. What is T sat? Minus 4 degrees Celsius. So what is the temperature of saturated vapor? Again, minus 4 degrees Celsius. How do you determine H1, HF, H4, H2, Hg? So initially, saturated liquid, finally, saturated vapor from here to there. Then H1 is going to be HF, H2 is going to be Hg. How do you determine HF and Hg? Oh, where's the table? At minus 4 degrees Celsius, HF, this number, Hg, this number. So HF, 44.75, Hg, 244.9. So if you solve it, you get the time. There's one thing you need to be careful here. What is the unit of this right-hand side? What is the unit of HgHF? Kilojoule per kilogram. Kilojoule per kilogram. And we have a kilogram here. So you can cross them out. What is the unit on the right-hand side? Kilojoule. What is the unit of voltage times current times time? Joule. So what you need to do? Multiply by 1,000 or divide by 1,000. Because one has kilo, the other part no kilo. Any question about this problem? If I give, so whenever you solve a problem, the first question you need to ask is, oh, if I see this one in my second exam, can I solve it? Not yet? No. Oh, because it says saturated liquid at the beginning and saturated vapor at the final. So they were given. One of the easiest problems in chapter 3. So you're kind of disappointed about the level of this question. So I prepared another problem which can be a little more challenging. Oh, that's not here. I forgot. Oh, the final answer? I don't know. But you have all the numbers. You can calculate that, right? So basically, whenever you have a closed system, the way to solve that problem thermodynamically is simple. Always write down the energy balance equation and find all the properties that you can. Then there will be only one unknown, then you can determine that. Then let's talk about the last part. So this problem, what is our system? Piston cylinder device? No, our system is R134A. is R134A, and the system that we used before, water. When you have water and R134A, they are phase change materials. So they become compressed liquid, mixture, or superheat vapor. So if you want to analyze those phase change materials, we need to determine the phase change process. That's why we draw this PV diagram, TV diagram to determine the phase change process. What if our system is a pure system? Pure system, like a pure gas, oxygen, nitrogen, or this cell phone, is there phase change? Must be awesome if there's a phase change. This become liquid, drink it, it poops out, and then cell phone again. No. So what if we have a pure system, pure gas, pure solid, and pure liquid? How can we, study them thermodynamically? Is there a table for pure system that we can use the same as the water or refrigerant, or is there another way to determine their properties? We can use specific heat, and this one is much easier than steam tables. So here I'm going to show you why. Specific heats are the energy, the amount of energy required to raise the temperature of the unit mass of a substance by 1 degree when volume is constant, CV, when pressure is constant, CP. So there are two different specific heat values, CP and CV. And if you go to the next slide, you can see specific heat relations of ideal gases, how this H, U, P, V, CP, CV are how they are connected. They are important, but I'm not going to do that here because we are not going to use this one until chapter 6. So when we go to chapter 6, we are going to talk about that again. So until then, don't worry about that. Let me just show you the solution. Then how there are two different specific heat, CP and CV. How can we use them? Let's talk about that. What is the energy balance equation? The general energy balance equation for closed system is Q in plus W in minus Q out minus W out is mass times U2 minus U1 plus moving boundary work. What about if we have a constant volume process? The right-hand side becomes mass times U2 minus U1 without moving boundary work. What about if you have a constant pressure process? The right-hand side is going to be, the left-hand side is the same. The right-hand side is going to be mass times H2 minus H1. Then, how can we solve these energy balance equations by specific heat? CP first. H2 minus H1 is CP, T2 minus T1. What about CV? U2 minus U1 is CV, T2 minus T1. Do we need to determine the phase change process at the initial state and also at the final state to evaluate U1 and U2? Not anymore. As long as you have a pure system, you can guarantee that there is no phase change. It's just gas or liquid or solid. Then you can use specific heat. You just need to know the temperatures at the initial state or at the final state, which can be which you can save time, right? So that's it. Now let's solve a couple of practice problems together to learn how to use them and how easy these are compared to phase change materials. The first problem, we have a spring-loaded piston cylinder device contains 1 kilogram of carbon dioxide. So we have a carbon dioxide. Is there phase change? Yes, when temperature is too low, but in general, no. So you can assume that the carbon dioxide is going to be just always gas, and that's a pure system. The system is under a heating process from 100 kilopascal at 25 degrees Celsius to 1000 kilopascal at 300 degrees Celsius. We want to determine the total heat transfer and the energy transfer by work. So let's do that. What do you want to do? Always number one. What equation did we study? Just one. Energy balance equation. So Q in plus W in minus Q out minus W out is, there are three of them on the right hand side. This one is constant volume, constant pressure, none of them. So which is the case? This one. Constant volume? No. Constant pressure? No. So we are going to use the first one. This one. Mass times U2 minus U1 plus moving boundary work. Then it's a heating process. Heat is provided to the system. So how can you determine the heat? Heat is provided. Q in. Heat is released. No. Is there energy transfer by work? No. No. What about this work? That is moving boundary work. Then, and it is pure system, pure carbon dioxide. How do you determine U2 minus U1? How do you determine U2 minus U1? CV T2 minus T1. CV T2 minus T1. We don't need to determine the phase change process at number one or number two. We can just determine this whole thing by CV T2 minus T1 plus moving boundary work is Q in, which is much simpler than phase change material, right? So whenever you have a thermodynamic problem, always the first thing you need to do is that, oh, is it phase change? Is there phase change or not? So when there's a phase change, you need to, use a steam table as we did in the previous problem. But if you assume that, if you assume that there is no phase change, simple as this, specific heat. Mass times specific heat. CV is specific heat at constant volume. CP is specific heat at constant pressure. So there are two specific heats, CP, CV. Then what is the mass? 1 kilograms. What is the initial temperature? 25. What is the final temperature? 300. What is the specific heat? Oh, how can we determine the specific heat? There's a table. CV of carbon dioxide is a function of temperature. So if you have table A20, then you can find CV at the given temperature. So now there is a problem. Initially 25, finally 300. So at which temperature we are going to evaluate this CV? 25? How many? 25? 300? None of them. We are going to evaluate specific heat at the average temperature. So what is the average temperature? 325 divided by 2, 162.5 degrees Celsius. So this is the temperature when we evaluate specific heat. So where is 162? Less than 250? No. The unit of this temperature is Kelvin. The unit of this temperature is degree Celsius. So we are going to add 273. So what is the temperature? 435.5 Kelvin. So where is it? Between these two. So when a value is between these two numbers, what do you do? Yeah. So the specific CV is going to be between these two numbers. Am I going to do that today? No. It takes time, and you know how to do that, right? So let's assume that it's going to be approximately 0.77 something. So this specific heat is from table A20. The value is, let's say, 0.77 kilojoule per kilogram degree Celsius. So we have everything but WB and Qin. So are we done? No, we only have one equation but two unknowns. So we need to come up with another way to determine either Q or W. Do we know any idea how to determine Qin? No. Do we know any idea how to determine WB? Yes. Really? Yes. How do we determine WB? There are 5 different ways. If you don't remember, one last time I'm going to tell you when it is, so how to determine WB. When it is a constant volume, then WB is 0. When it is constant pressure, WB is going to be pressure V2 minus V1. When it is constant temperature, WB is going to be PV natural log V2 over V1. When none of them, it's a polytropic process, PV to the power n is constant, WB is P2 V2 minus P1 V1 over 1 minus n. None of the case. PV diagram. And usually when we have a spring-loaded piston cylinder device, in one of the previous problems, we used this graph. Because when you have a spring-loaded piston cylinder device, this one is a straight line. I think we discussed that by using force analysis. I'm not going to do that again. You can find it from one of the lecture videos. So here the same, we are going to use a graph. T3 diagram. What is the initial pressure? 100 degrees Celsius. Here, 100. What is the final pressure? 1000. And what is the volume? Oh, we don't know the volume. So what we are going to do? Give up? No, no way. We can use another equation. So do you remember any equation that has V in thermodynamics? We didn't study many equations. There are only, the less than 5. We have 5 fingers, so you can memorize 5 of them, right? No. Energy balance equation, we wrote it here. Yes. The ideal gas equation. PV is mRT, or P1 V1 over P1 is constant. But in this case, we can use PV is mRT. This one at the initial state, P1 V1 is mRT1. At the final state, P2 V2 mRT2. What is the mass of the system? 1 kilogram. So this one is 1 kilogram. 1 kilogram. What is the initial pressure? 100 kilopascal. What is the final pressure? 1000 kilopascal. What is the temperature? Initial temperature, 25 degrees Celsius. The final temperature, 300 degrees Celsius. How do we determine gas constant R? R of carbon dioxide can be determined by universal gas constant R bar divided by molecular weight of carbon dioxide. Universal gas constant is always 8.314. The molecular weight can be found from here, carbon dioxide, 44.01. So that's how you determine R. And this R goes in here and here. So if you solve these two equations, you get V1, V2. Am I right? No. What is wrong here? Kelvin. 298 Kelvin, 573 Kelvin. Anyway, either way, you can determine V1, V2. So what is V1? 0.52 or 5629. V1, 0.5629 cubic meters. V2, 0.1082. Not yet work. So this is the initial volume from this PVMRT. This is the final volume from this PVMRT. And here is the initial state. Here is the final state. So if you calculate the area here, you can determine WB. Then how do you determine the area? 1000 plus 100 divided by 2 times these two, 0.5629 minus 0.1082 is moving boundary work WB. The area, absolute value. So the area is going to be what? 250.1 kilojoule. So that's the area. So going back to this energy balance equation, here, WB is 250.1 kilojoule. So you can determine Q in. Is this right or wrong? You have 50% chance to be right, right? Wrong. Yeah, you're right. Then why? Why 250.1 kilojoule for this energy balance equation WB? Why that is wrong? Because, yeah. Yes, it's a compression process. So area is this one, but when you put this one, you need to add negative sign because it's a compression process. Initial volume this much, final volume this much. Then you can determine Q in. What is Q in? Minus, I don't remember. You get the number, minus something. Then why there is a negative sign if it is Q in? That means there was no Q in, there was Q out. So depending on the sign of Q in and Q out, you can check whether it is incoming heat transfer or outgoing heat transfer. So if you made a wrong assumption that there is a Q in, if you get the negative value, then you can say, oh, there was a Q out. That's how you solve this problem. Any question? Too hard? Too difficult? If I give you this problem in the second exam, can you solve it? Not yet? Okay, then the next problem is going to be a little simpler than this one. I knew some of you can say not yet, so the next problem is easier than this one. So 30 seconds. Done? Okay. Not yet? Okay. 20 seconds. Here's yours. Then the next question. We have an ideal gas contained in a piston cylinder device. undergoes an isothermal compression process, which begins with an initial pressure, volume. So we have pressure and volume at the initial state, and there's a heat transfer to the surroundings. So Q out of 60 kilojoule determine the volume and pressure at the end of this process. This is a super easy problem. So let me show you why it is super easy. The previous problem was just process, but this time isothermal process. When you see constant volume, constant pressure, constant temperature, they are super easy. Then what do you want to do? We need to determine whether it is phase change or not. Ideal guess, oh, it's not a phase change material. So it's a pure system. When you have a pure system, let's write down the energy balance equation. Q in plus W in minus Q out minus W out is mass times U2 minus U1 plus moving boundary work. We know there's a Q out for the amount of 60 kilojoule. So this one is a 60 kilojoule. There's no W out, W in, Q in. So there's a negative sign in front. Minus 60 kilojoule is mass times what? U2 minus U1. How do you determine U2 minus U1? This time we know we are going to use specific heat. CV, T2 minus T1, plus it's a constant volume, constant temperature process. How do you determine moving boundary work? Constant temperature process. PV ln V2 over 1, V1. PV natural log V2 over V1. That's for constant temperature. PV natural log V2 over V1. So we are ready to solve this problem. What is the process? Constant temperature process. What is the relation between T1 and T2? They're the same. So this folding 0. So minus 60 kilojoule is PV natural log V2 over V1. Since we know P1 V1, I'm going to say P1 V1. So this is 100 kilopascal. V1 is 0.6 cubic meters. V1 is 0.6 cubic meters. Can you determine V2? Yes. From this, V2 is 0.221 cubic meters. By the way, sometimes I give you the answer. Sometimes I don't, right? Why is that? Because the solutions to many textbooks are incorrect. So this one was correct. The other one in the previous problem was incorrect. So if you look at this one, you see I mark them. This one is wrong, and the real one is this one. The real one is this one, like that. Do not believe the solution. There are many, many mistakes. Yes. Oh, you can have it. Let's recycle it. Can you recycle it? Yeah. So once you determine V2, now we need to determine P2. How can you do that? When you have a constant temperature process, what is the relation between P and V? Do you remember that? It's an ideal guess. T1 V1 over T1 is P2 V2 over T2. It's a constant temperature process. T1 is the same as T2. What is P1? 100. What is V1? 0.6. What is V2? 0.221. What is P1? 272 kilopascal. That's how you solve this problem. We have 2 minutes. So what can we do in 2 minutes? We can leave early, so we can have our full break starting from now. Oh, I'm sorry, I don't have class tomorrow, so I will be gone.